Hello, welcome back to AE 2220. In this video, we are going to cover some special cases for rectilinear motion as well as relative motion between two particles. We're going to start by talking about uniform rectilinear motion, and this is a type of straight line motion where the acceleration is equal to 0 for all time. And just in case you haven't seen this upside down A, this means for all values of time t. So uniform rectilinear motion is straight line motion where the acceleration is equal to 0. This tells us then that the velocity will be a constant. And the reason is that the acceleration is equal to dv dt, or the time derivative of the velocity. And we know that this is equal to 0. And if the derivative of a quantity is 0, then this tells us for always 0 is exactly equal to 0, not just at a particular time, but for all time. This then tells us that that quantity itself must be equal to a constant, because the derivative of a constant is 0. Now, if the velocity constant is equal to 0, then we have the body at rest. There is actual no motion, so this needs to be non-zero. So the velocity cannot be equal to 0, but it is a constant. Then, since we know that v is equal to dx over dt, if we multiply both sides by dt and then integrate, we will be able to find the position. And that gives us the integral from x0 to x of d c, that's our dummy variable, is equal to v times the integral 0 to t d tau. That's our other dummy variable for time. And you'll notice I pulled out the velocity from the integral, and the reason for that is because it's a constant, so it does not depend on time, such that it can come out of the integral. And then we get that x of t must be equal to v times t plus x0, that initial position. Let me try and box that again. There we go. Okay, so this is only true. This equation is only true if the acceleration a is equal to 0 for all time. That is the only case where it's true. And let me write that in blue, just so that it appears different. This is by far the simplest case of motion, because as I said, if the velocity is also 0, then you don't have any motion at all. In fact, that is the definition of rest, that both the acceleration and velocity are 0 for all time. The next case we're going to consider is that of uniform accelerated rectilinear motion. This is a type of straight line motion where the acceleration is a constant. Acceleration is a constant, and it is not equal to 0, because we just did that case. So it's a non-zero constant. And this is, a case of this is any body in free fall on any planet or planetoid. Any body in free fall is under a uniform accelerated rectilinear motion, or experiences and undergoes uniform accelerated rectilinear motion, provided that it's in a uniform gravitational field. If that gravitational field is changing, if you're counting for like distance from the gravitational center, for example, then it's a little bit different type of motion. If we assume uniform gravitational acceleration, then we have uniform accelerated rectilinear motion for a body in free fall. This is not a projectile motion, this is just a body in pure free fall. So in this case, we have that the acceleration equals dv over dt, which is equal to some constant. We can go ahead and multiply both sides by dt and then integrate, and we'll get the integral from v0 to v d special v equals a times the integral 0 to t d tau. Again, these are our two dummy variables. And then we'll find that the velocity here as a function of time is equal to at plus that initial velocity v0. So here we have a velocity that is now a function of time, varying in time, because that acceleration is no longer zero. We can then go ahead and do the same type of integration with the velocity in order to find the position. So we know that the velocity is equal to dx over dt. We'll multiply by dt and integrate again. In this case, we won't be able to pull the velocity out because it's now a function of time, although that v0 is constant, so we'd be able to pull that out. But nevertheless, we will get that the integral from x0 to x d c is equal to the integral from 0 to t of at plus v0. That's our velocity, d tau. And what we'll find then is that our position, x of t, is equal to 1/2 a times t squared plus v0t plus x0. There. And that is our position as a function of time here. And you can see in this case that it is a polynomial with respect to t squared, a second order polynomial with respect to time, that it involves the constant acceleration, the constant initial velocity, and the initial position. With that, we're now going to move on and take a look at motion of multiple particles. Specifically, we're going to look at relative motion, relative rectilinear motion, specifically of two particles. We're going to consider two particles, A and B, that are moving on the same line. Let's go ahead and we'll draw our line here. Positive direction to the right, we'll just say that is the direction x. We'll have particle A here, particle B here, and then we're going to assign the origin over here to the far left. And let's extend this line down because we're going to use that to dimension things. So first of all, the position of A, let me erase that. We're going to call this position XA, measured from the origin. Measured from the origin to A. And then we're going to have a position XB, measured from the origin to the position of B. And then the relative position depends on which particle we are talking about. So the relative position of B with respect to A, we will start by drawing from position A to position B. And we'll write this as x B/A. If we want to talk about the relative position of A with respect to B, we would consider that as the position from particle B to particle A, and we'd write that as XA/B. And that means the position of A relative to B. So we will write that out over here, XB/A. This is the position of B relative to A. And then XA/B, this is the position of A relative to B. Okay. What we can then say is that the position, and I need to make a little bit more space here. We can say then that the position XB, this is going to be equal to, starting from the origin, and I'll draw with a laser here. If we start from the origin, it's going to be equal to XA plus XB/A. XA plus XB/A. So or the position of A plus the position of B relative to A. From there, we can solve for xb slash A, and this is equal to xb minus xa. And likewise, we can do the same for xa slash b. Xa slash b will be equal to xa minus xb. We can do the same thing for velocity and acceleration. We will find that vb slash a, this is the velocity relative to velocity of b relative to a, is equal to vb minus va. And then for the acceleration, vb slash a is equal to a b minus a. And then we'll do it for a relative to b, so va slash b is going to be the negative of that, or va minus vb, and a slash b is equal to a minus ab. So here, because we're in a rectilinear motion, these are all independent of that motion. And that's because we're considering rectilinear motion. This changes when we're dealing with non-rectilinear motion, and we'll particularly see this when we get to dealing with rigid bodies, where we want to express the velocity and acceleration of one part of a rigid body with respect to another part of that rigid body. But for rectilinear motion, these are independent of that motion simply because we are moving along a straight line. And this relative position also becomes useful and important for when we deal with trying to compute the force across a spring that is connected to two particles or 2 points that are moving. Okay, we're going to go through and do an example now for considering this. A particle accelerates at an acceleration equal to 3t, and we're asked to determine its position, its velocity and position for initial conditions of v0 equals 2 and x of 0 equals 4. Okay, so in this case, this is an example of this uniform, actually it's not even uniform accelerated rectilinear motion, because now we have an acceleration that varies with time. But we can apply the techniques that we've been working with, where we've been integrating to this problem as well. So first, and so I wanted to also say that in the introduction, I talked about the fact that we're going to use a problem-solving algorithm. For rectilinear motion, there is only a single direction, so we don't need to go and define a proper coordinate system because it's always going to be in the same direction. Once we get into non-rectangular coordinates, that is where we'll start dealing with this type of issue, or in fact, even when we're dealing with curvilinear motion and so forth, that's when we'll start to need true coordinate systems. But pure rectilinear motion, we do not need to go through and do this problem-solving algorithm. Okay, so in this case, we'll have a of t equal to, here it's a function of t equal to 3t. We are then going to go ahead and we'll say that a is equal to dv dt. From there, we'll split this up and integrate both sides. We'll have the integral from v0 to v d special v is equal to the integral from 0 to t of 3t d. In fact, I forgot the dummy variable here, so this should be 3 tau d tau. So you can see when we have a dummy variable, we are switching that out for anywhere we see t. So we want to integrate from 0 to t, so anywhere in our acceleration function or function we're integrating, we're going to switch t for tau. Extending this, we'll find that the velocity must be equal to the integral from 0 to t, 3 tau d tau, plus the initial velocity, which is 2. And then we'll find that the velocity, function of time, is equal to, well, if we integrate this, we're going to get, if we integrate this expression, we're going to get tau squared divided by 2, so 3 over 2 tau, evaluated at t and 0. So 3 over 2 times 0 is 0, and 3 over 2 times t is exactly that. So we get, and it should be squared, tau squared. 3 over 2 t squared, that's where the 1/2 comes from squaring that, plus 2. And that is our velocity as a function of time. I'm not sure what happened with my square there. Okay, now that we found the velocity, we now want to go and repeat this integral and this integration approach to find the position with respect to time. So now x of t is equal to the integral from 0 to t, v of tau d tau, plus x at 0. And you can see that we've already done the integration for the x here. We just skipped that step. It's the same as what you've seen previously. So we'll then get the integral from 0 to t of 3 over 2 tau squared, again using a dummy variable, plus 2 d tau, plus, and our x0 was 4, so we get plus 4 here. Okay, so what we'll then end up with, x of t is equal to, evaluating this integral, we're going to get tau cubed divided times 1/3, so we'll get rid of that 3 in the numerator, so we'll get 1/2 tau cubed plus 2 tau. And this is evaluated at 0 and t, plus 4, and this will then be equal to 1/2 t cubed plus 2t plus 4. So our position as a function of time, x of t, is now equal to 1/2 t cubed plus 2t plus 4. And that is the solution to this example problem. All right, in the next video, we're going to start curvilinear motion of particles.